All right, I think that might be everybody. Not sure. So welcome to the largest STEM Physics Club meeting. I'm Timothy Shi, ninth grader at Melbourne High School, and I'll be presenting to you the three Newton's laws today. So I don't want this class to be really boring and monotonous. So I'm gonna ask some questions along the way um, of the class. So um, be prepared to answer some questions. Uh, so if you do not really want to participate, you can always just like, I don't know, like private message me a one or something. Yeah, just private message me a one and then uh yeah, you can like that. Um so yeah, if you have any questions at this stage, feel free to ask anytime really. So yeah. So today's agenda will be we're gonna first discuss Newton's laws. I'm gonna explain to you and elaborate a little bit more on them, explain to you the basics of them, and then I'm going to then explain some limitations on these laws, and then we're gonna do like 4 or 5 problems on them, and these are discussion problems, so I don't want like an answer for them. I want like an explanation and a sufficient answer. Like I'm not looking for an answer at all on them. I'm just looking for how you solve the problem and how you get to that solution. Right. First law is an object stays in motion unless acted upon by another force. This law is probably very self-explanatory, but basically what it means is that if we have an object and it's going to go in one direction and nothing else affects it, it'll keep on going forever, nonstop, just keep on going in that one direction. But when something else acts upon it, this will change because there's another force acting upon it. So um this force may be friction. So like a common misconception of this is you're gonna roll a ball on the floor, it's gonna eventually come to a stop. That's because of friction. But that's because friction is the force that acts upon this ball. Um, but in a perfect experiment, no forces, nothing. It's going to forever and yeah, just goes on forever. And in this second diagram right here, this one, um, you're gonna have that ball, and then let's say that it goes for some time, and then there's another force that is the wind. It's going to act upon this ball. That will change the ball's direction because it will have another force acting upon it, and then the resultant would be a change of direction or maybe even stop sometimes. Like if you go into a wall, well, that's the third law, but yeah, uh, if there's another force acting upon this, it can change directions or it's it's not going in motion in the same way. All right, let's go to the next slide, which is the second law. This one is a formula. It's force is mass times acceleration. So force is represented by newtons, and the standard unit, uh yeah, that's the standard unit, and this ways this can be applied to an object. They can be applied like if I have my hand here, it can be applied like this, or um um like a magnetic reaction, it can be applied at a distance. So like you can have a magnet and something else applying the force on that object to change it in some way. So some very common of force, I force, the one that I just showed you, it's interacting with the object, magnetic force, drag, gravity, and friction. So uh, friction is very commonly missed one, and it will, how do I explain this? So friction will apply. It's almost a force that's applied the entire time on an object. So it will keep on applying this force, and that's why it's almost always commonly missed. Same with gravity, it's also commonly missed force. All right. So let's talk about acceleration in this equation. So acceleration is change in speed time. Is that from, say, is at, it's gonna subtract y and absolute uh that's in speed, and that's over an amount of time. So your acceleration should be the change in speed over the time elapsed during this change in speed. Um, so the formula is for acceleration is change in speed over time, and acceleration, it's like definition would be the result of a non-zero net force, which means that it's this object has inertia, it's going to keep on going, but then it has something other than zero, a force acting upon it to make it go slower. Uh, this accelerator would be like when you, so are you're driving along a road, maybe you're gonna just keep on going. Suppose this road has no friction, there's no um, air resistance, and then the car is just going. You're not pressing any pedals; it's just going at this constant speed. If you add acceleration and maybe like a gust of wind pushes the car a bit more, that's an acceleration over a very small period of time, where the car will go faster, and then it's going to stay at that speed because of the first law. So in our diagram here, I've put a ball here which has a mass of m, and if there's an acceleration of a, then the force acting upon the would be f. All right, let's talk about the third law now. So if an object A exerts a force on object B, then object B will exert the same force F back onto A. So when you're looking at basketball, it's a sport with a lot of jumping and running and all that stuff. So um what happens when they jump, this is a very specific example, but what when they jump, they put a force into the floor. Like this, like when you're jumping, you think of putting a force into the floor to propel yourself upwards, but that's not actually the case. It's um you're putting it onto the floor, but the floor is actually propelling you back because that force that the floor puts onto you is to what you the force. For just go to zero, or effect to zero, the floor just, and the force or F where actually gonna go up because the the force is what's propelling you going up, and your force that you exerted onto the floor kind of just disappears when you have exerted it. So I think a great example of this in action, another one of them, is a pitcher throwing a ball at the batter. So when the pitcher throws this ball, he's going to exert force onto the ball, and in return, the ball pushes his hand back too. So when you think of it, you're going to be pushing a ball, and when you push that ball is exerting the same amount of force onto your hand, and that force exerted onto your hand is going to affect you and the ball. So you're effectively pushing your hand back and the ball to the the batter, hopefully at the same time. Um, basically, for each fly there forces that come into this. Um, let's some example. Um, Angela, please example. Uh, if, and you can choose when they come into effect.
Timothy, you're lagging a lot.
Hmm. Did you catch what I said?
It's sort of like laggy, so sometimes I don't catch what you say.
Okay. Can you tell me what I kind of missed? I'm sorry.
So about the formulas and things.
All right. This one, right? Oh. All right. Wait. Give me a second. I'm gonna go try and fix. All right. Just whenever I cut out, can you guys just like tell me or something? I'm not sure what cut out, so yeah, because I'm just talking and talking. It's well, when I cut out, I don't really know that. So please be sure to tell me if I cut out, and yeah, I can just re-explain it to you guys. So um, in Newton's second law, we went over the formulas of um force, and we also went over the formula of acceleration. So force, mass, acceleration are formula that is the second law, but acceleration is a part of this formula. Acceleration is a derived unit from speed and time. Um, acceleration is change in speed over the time elapsed. So um if you're going to have a change in speed, that's going to take place over a period of time, and you take those two, subtract them, and then uh put them over the elapsed time, and then that will give you your acceleration. And the basic unit of acceleration, well, the SI unit is um meters per second squared. And it's second squared because it's going fast in a time. It's not your speed. Sorry, it is changing, not your distance time. It's Uh, again. Mm, sorry. I can try to talk a bit more slowly so if it's not gonna affect it as much. Um, so most people confuse speed with acceleration. So speed is distance over time because of our formula distance equals to speed times time, and then we take the time and divide it on both sides. We get this speed. Um, so acceleration change speed over time. So that's where we have seconds squared instead of just seconds. Um, and acceleration is the result of a non-zero net force, which means that when you have an object that's still, there's obviously multiple forces acting upon it. There's gravity, there's maybe friction times, there's many just act, but net is zero. It's net of all of if that then it's zero. Like, a very per case, which me okay, I think I'm cutting out again. But it's near perfect, which means that the net force is very close to zero. And that's what makes this object stay in place because all the vectors have added up to zero. All right. So can one of you guys give me an example of the first, second, or third law? Just any of them. We can talk about it and discuss because this is physics is a very um interactive thing. It's not just me talking monotone. So yeah, how about Thomas? Can you give me an example of one of the three laws? All right.
I could give one.
Yeah, go ahead.
So I think Newton had a law about that if you have an object and it's moving without any force stopping it, then it would move on forever. But if you have some type of force that is intercepting the object, then it would go in different directions or slow down.
Yeah, that's exactly this law. Um, so you like a actual in like maybe a car or something. I don't know. Just do you want to give me a real life example?
Suppose you have a uh, ball and you push it around, and this ball is going to move on forever without like without any other forces. But if you have some type of other force uh, like the wind or the grass that is rough, they sort of like the ball gets slower as it's moving forward.
Yeah, that's actually the example I wrote down was hockey. Um, there's the hockey. There's like um the difference has a lot and then the us, and that has a huge impact on how the game is played because there's so much friction there, and that'll change how the ball moves or the puck. Yeah, the puck moves. Okay. I got a private message talking about the second law. So They said that riding a bike is a great example of this law. That is actually a very good example. Anything with vehicles is a good example in the second law because when you're uh exerting a force and you're going forward, I can your amount of you bike and excel of that um the um yeah, I kind of got into a YouTube rabbit hole of biking, and it was talking about how um m- how bikers would like change positions in how they ride the bike, and it didn't have that much of an impact on their speed, and it's only because of the aerodynamics. So the acceleration, everything is still the same in this equation. It has no effect on the biker. How much, like if they're giving the same amount of force, it's not going to affect them. It's just the aerodynamics that might affect them a lot. All right. Does anybody else want examples? Yeah. Okay. Probably putting a ball. So this is it's application of a lot of these laws. So say third law. It could. I think you're talking about the third law. I'm not sure, but if you let's say that this red thing is a ball instead, so you're gonna have the ball. Oh, it's yeah. So you drop the ball, and then it's gonna go down onto there, and then it's down. Zero force onto there, and then that force is going to be drawn back up for the ball. So the ball is going to go back up because of this force. Obviously, there is a universal fact of gravity pushing down on this ball, which means that each time the ball bounces, it's going to get lower and lower. That's because of gravity, um, like kind of holding the ball down like this, which is also an application of the first law. Because if the first law weren't true, then the ball would just be down, up, down, up, down, up entire time. It's not going to change at all because you're going to have a force going down and that same force going back up, and a force going down, the same force going back up, down. That's if the gravity is super small way that it's going down. Actually, if you're gonna force on to the ground, it's gonna bounce up, down, down, up, down. Yeah, that's a great example. Because it incorporates multiple of these laws. Yeah. Um, does anybody want to give me another example, or do you want to move on to the questions that I prepared? All right, I guess we can just move on to the. Oh, okay, I got another one. So this one is the third law. It's punching a wall and getting hurt. And this is a very common example because whenever you get hurt, the third law is deploy. Let's say that this hand is going. So it goes into the wall. That means that your force goes that way, and this wall right now, there, it pushes back onto your hand, resulting on a force that goes into your hand, and your hand absorbs that force, making you get hurt. It's a huge chain reaction because it's you're gonna punch the wall, and then it's gonna put the force in, which in response gives a force out, and then that's gonna impact with your skin and then your flesh, and then it's going to uh most likely, yeah. So that's, yeah, that's example third law. All right, let's move question that I prepared. Oh, wait, I forgot. Okay, so we can also talk about vectors, but I kind of already explained this. So vectors, whenever I drew those lines, eh, this is a vector of force. So whenever you're using vectors, you're going to um place it at the origin. So think of this as a plane. Place it at the origin. So let's say that this is just going in the x-axis. And this is a force of uh force of magnitude F. So this force is going in the x direction with a magnitude of F, which means that its ending point would be, sorry, F0. Oh, okay. So how do we solve vectors in math? So, yeah, vectors are a very mathematical part of physics where it takes some trigonometry, but I don't think I have to really show you the trigonometry for you to actually understand it. So when you have a vector going here maybe and a vector going here, right? So let's say that this is like 5 and this is 3, right? Then we have, oops, so we have 5 and 3, right? The thing that most people would do would to be draw a line there and get a triangle, but that's actually not correct. So when you're adding vectors, so I guess when you said you have to solve a vector in math, um you're gonna have a 3, you're gonna put it over there. So when you add vectors, you can add them on top of each other. So if you have vector going this way, a vector going that way, a vector going that way, a vector going that way, whatever, right? When you add all those vectors up, it should come to this, and then you put this vector onto there, you put that vector onto there, you put that vector into there, and that gives you this point, right? And then even if you flip all these around, do random stuff with it, and there's obviously they still have to face the same direction, you're still gonna arrive at this point, and that's how we add vectors. So basically in this plane right here, right, we're going to have a vector 3 and a vector of 5, of magnitude 5, and then we're going to place this 3 vector over on the n5 vector. So I'm going to redraw this, and then we put the 5 here, we'll put the 3 there. That means that this is our ending point, right? And the logical way to go is this 5, 3, a point on plane, which is a coordinate of x and y, but we're actually using this for vectors, so it's actually very useful in many places. So since we started from here, our total displacement, which is every vector added up, right? Our displacement is this. Now this is easy because this is a right angle right here, right? So we're going to use the Pythagorean theorem to get 25 plus 9 is, oh yeah, let's make it a little bit louder, is a 25 plus 9 right here is 34, and then root of and which value. Right? That's our vector is. Now there's sometimes when this vector is not a 90-degree angle. Let's say we have this, and then we have a vector going in the x direction, say 7, and a vector going like this. Let's say that this is a 50-degree angle, right? If it's going to go in that direction, that means that we can always add this vector onto this vector, which we did in the previous problem. And then we're going to put that there, 7 there, put that there, up. I'm going to give term like that doesn't right. Say 9. So this vector is a magnitude of 9. So this right there is a 9. Our total displacement right here is, oops, that's not a very good line. Is this. Now, the best way to go about this is to calculate this point right here, right there, put that line there, and then get this point, and you're gonna get excuse sorry, some number and 0, and then we're gonna use our trig functions to find this side length over there of this triangle. I'm not gonna get into that because this is some trig math, so I'm not sure if all of you can do this as of right now, so I'm not gonna go over it, but I'm just gonna say that there is a way to do this. Maybe you could learn this when you're in algebra, because it's just kind of memorizing it, but just for trig function itself story. This is as I'm with this because they're not easy to understand, and I want to give like a 3-hour lecture on this. It's gonna take forever, you know. All right. I think it's time we can move on to our problems. If you guys have any questions about this, I can answer them right now. So do you guys have any questions on this? Vector addition it's not very easy, so I wouldn't be surprised if you have any problems.
I have a question. So, what's the relationship to Newton's laws?
Okay, so you know how Newton's laws have to do with force? Like in our first law, it has to do with force stopping or like an object that is always in motion. And then our second law having to deal with force itself, its equation F equals to ma. And then our third having to do with um the receiving and giving of force, right? So all of these have to do with vectors because vectors is one of the most fundamental methods in physics to find out a value of force. So if you're given a value of force this way and a value of force that way, then you know that this is going to be your total of forces. Also, another place where this has to do with the Newton's laws is our net force. So when we calculate this, there, I drew the same diagram again. Okay. Um, when we calculate this is the net force, which means it's going to be our displacement. That right there is our displacement to this point over here. So displacement, if you need me to elaborate, so this is our start point, this is our end point. You can go anywhere. You can go right there, there. But if you end at this point, and then this right there is your displacement. And it's kind of like this vector, because our is a part our law, right, our law and our law has some the third a little bit, not that much. All right. All right. It seems like we can move on to the problems now if you guys don't have any questions. I'm just gonna give you a cheat sheet here. So for these questions, you don't have to worry about dimensional analysis because I'm not giving you units in these. So these are our three laws. Here are actually to the questions. Let's talk about applications of physics, because this is a very broad subject. You know, physics, there's so many things in it. But there are some limitations on the entire thing itself. So physics is based on human observations. It feels like a disclaimer actually, but like it's based on human observations and what we can observe, which means that what we can't observe isn't these laws, or most, or maybe all, don't work in actually we're not sure if it works. I'm going to put it that way. We're not sure if it works with things that we cannot observe. Things we can observe can be observed with like tools and all that stuff, but things we cannot observe cannot be observed with any tools. Humans just cannot observe it in any way. Like smell, we can observe it, well, five senses. Come on, five senses we observe, and using tools we can observe things. But when we're in a situation where it's something that we cannot observe, that must mean that there's something that we're missing and we can try and find that out, or um the basic physics rules may not apply to it. And this has to do with vacuums and environment, because vacuums are one of the steps in trying to achieve a perfect space where there's no outside factors affecting it, and that's our environment, what we live in, what's around us. And yeah, so let's go to uh, for these ones, I think I said this at the beginning, but I do not want you guys to just give me an answer like yes or no. I want you to explain your process to the answer and maybe like apply some of these rules, because these all are all based on these rules. When I wrote model here, I'm just talking about a perfect situation where uh, uh where minimal factors don't come into play. All right, my handwriting is really bad. Um, so yeah, I'm gonna give you a few minutes. You can try out these problems, and yeah. So let's just focus on number one. It's looks super easy, but I want you to explain it to its fullest. So I'll give you just like 1-2 minutes. If you need any more time than that, then just say so.
What does equilibrium mean?
Just a term like equilibrium is of zero. I know
You're lagging.
nothing. All right, I'll text you this in the chat. All right, you can see that, right? That's good. All right, so our first problem. So the balloon is in air and it's not going up nor down. Is it in equilibrium? First, this is yes. Um, but if I was to play the scummy way, it would be no. But like in this case, I'm gonna say yes to it because um gravity is affecting it going down, and the balloon is staying in that one spot, which means that the net force going up and down is isn't only up and that it, unlike a very test, it's not in equilibrium truly. There could be forces affecting it sideways. So this, so F1, F2, F4. So from this problem, we know that F1 plus F2 equals to 0. So if I were to draw a coordinate plane, um, F1, F2, those add up and they're the same, which means that in this state, they're in equilibrium. I didn't give you these, F4 and F3, not just that it's in equilibrium. Any other effect in obviously space, so there would force going that way, maybe, and force going this. Um, but yeah, this is correct if you give me the right reasoning, and if you count for this. So for the second one, um, so the balloon is in air. It's not going up nor down. What are the forces acting upon it? I just showed you that. I think, um, the forces acting upon it are F1 and F2. Right? F1 and F2 are acting on it. That's no. I don't know. So it's gonna. I'm just F1 and it's fine. Now let's talk about 3. So you're in a car, you're moving, and there's a sudden stop. So why do you pitch forward? This is actually a very common one. So when you like slam on the brakes, you're gonna pitch forward. Because physicists are, they always ask, we pitch forward because of inertia. So we're going at this constant rate, and then suddenly, like, you have to go that way. So the leftover force is going to still go that way, and then you're going to pitch forward while your car is stopped. So that is our first law, because um we were going straight line disturbed, so there's a vector in direct in the opposite direction, which he stops it, and then the objects inside the car pitch forward. All right, that's a bunch of vectors, random vectors, but I think I'll explain it should be fine. Um, this fourth one is the same thing. Also, yeah. So the fourth one is you're falling. So you're going down the y axis. And there's a sudden stop. And then let's say that this is not that big of a height, so it hurt you, it didn't kill you, right? But what it because down, but it stopped that hurt you because when you fell down, you exert a force onto the ground, and the ground exerts the same force onto you, and then you are taking the full force of that drop. So when you take the full force of the drop, it's not actually you that's exerting force onto yourself and getting hurt. It's you exerting onto the ground and exerting force on you, and you're taking the impact of that collision of forces. While the ground is obviously unsathed. Yeah. So do you have any questions about this class?
So what is this class going to be based off of?
So this is a physics class, like be talking a bunch of topics within physics. Obviously, some of these topics may be harder, some of these might be easier. Most of these topics will be the ones on the test F equals to ma, which is one of our laws. Actually, it's actually kind of funny. But it's a test. See if I can pull its website up. But I can't really find it, but like it is a competition. It's like, you know what AMC 10 and 12 are. It's a competition like those. It's the United States Physics Association. Yeah, basically USA Physics Olympiad. Yeah, it's basically AMC 10 but for physicists. All right. I got a question in the chat. So if you fall down from a taller place, is there more force, and is that why it hurts more? Yeah, that's exactly it. Because remember, so falling down with one, right? And here's the ground. Can we draw a straight line? That's good enough. So you're gonna hit the ground, and then that force is I'm gonna draw this in a different color. That force is going to go down, and then that's, and then in the going to see this here that is affected onto you. So basically, when you fall down, this force goes down into nothingness. So it doesn't change. It just effectively is out. This force right here affects you, which hurts you. Yeah. So I got another question. When you're falling, is it the velocity or acceleration that determines how much it hurts? It's a great question. Me go. So this is kind of an application of both our third and second. Okay. Yeah, you answered it correctly. So this is a very common misconception. Um, it's not your velocity or your acceleration. It's your velocity and acceleration is going to go into the ground, and the ground that gives you the shock back is what's hurt you. Um, so if I punch myself right, punch my hand, use the punch that is this, but it hurt the punch it because has received a with school punch and punching the you and you you punched their with your face, and they punched you your face with their hand. It's actually kind of funny because I was reading a comic and this is one of the things that was in it. So um the victim was complaining about the bully, and then the bully responded with his stomach punched my hand, which is technically true because of the third law. Um, yeah, higher velocity equals higher deceleration. Um, I guess if that's how you put it, but remember that it's not the velocity that hurts you in the end. It's a it's derived from your velocity, but it's not actually your velocity that hurts you. It's first that back from this and you could ground really when you use the ground blow. Third level, it down and then goes back up, which hurts you. So it effectively you can blame Newton for hurting you every time you get hurt. All right. All right. Do you have any more questions, guys, girls? All right. If you don't have any more questions, I think that's it for this meeting. Um, feel free to come to the next one. I'm not sure if it's going to be as this one. There was time. Uh, should be 6:30, 7:30 is more time for these. I'm free. So come and thank you for this meeting. Bye.